Okay. Hello, everyone. I'm glad to be here. I'm glad to be the first one. What I'm going to talk today will have pretty much nothing to do with the reverse math. Okay. So the idea is, well, as computable structure theory is not the main topic of this summer school, so I will give a general introduction. So starting with a very basic facts and like an overview of what's going on. And well, at the end, maybe tomorrow or on Wednesday, I will hint how you can do some reverse mathematics in this context. Okay, so in particular, I will assume no knowledge of computable structure theory. Yeah, so I assume that you know some basic logic, like basic computability, basic model theory, maybe some basic algebraic facts, but nothing about mixing them. Okay, so if you already know something, then stay with me till later lectures. Otherwise, if you have any questions, if I go too fast, maybe, then just let me know. Okay, so when we talk, so basically we're talking about effectivizing some mathematical objects, right? And there are two points of view how to do it. We start from theories, and we effectivize theories and look how models of those theories look like. Or we start with the structures, and we effectivize structures, and we look what's going on if we start like this. So today I will start from the theory side, which is probably, historically seen more natural. And tomorrow we'll do the other side. We'll do the structures. Okay, well, what are the main definitions here? Okay, so first of all, our languages, well, we'll mostly probably consider finite languages just to avoid confusions, but in general, we'll consider languages that are computable, like possibly countable, or at most countable or finite computable language. What does it mean? It means that, well, if it's finite, then it's computable. And if it is infinite, then there is a function that basically gives us, in a computable way, the arity and the type of the symbol. So the symbol number S has arity and S, and this is a relation symbol, for example. Yeah, so this is a computable function. Okay. But mostly we will consider just finite languages. At least examples will be in finite languages. We'll see if it's infinite. Well, let's see. Okay, and well, a theory is okay. So we have a computable language, and it means that we can then effectively enumerate all formulas in this language, the standard way, the Gödel numbering of all the formulas, right? You know that, right? Okay, so we have a Gödel numbering. Can you see what I write, or should I write bigger? Fine, okay. Gödel numbering of L formulas for whatever language we have. And so by doing this, we identify formulas or sentences with natural numbers. And we can talk about computable or whatever computability theoretic complexity set of formulas of sentences. Some particular decidable theory, a theory. T is decidable. If it is a computable set of sentences. If, well, formally the set of Gödel numbers of sentences from this theory is a computable subset of the natural numbers. Yeah, omega for the natural numbers. Okay, so in particular, when we talk about theories, decidable and computable is pretty much the same thing. Okay, so we can, and I will probably mix them. When we talk about structures, this is not at all the same. And for structures, you know, we have to be careful. If we're talking about decidable structures or computable structures. For theories, it's like this. Okay, so this is for theories. What about structures? Okay, when we talk about structures, then we need to expand our language. So suppose we have a structure M, let M be an L structure, and, well, the structure looks like some universe, and then the interpretations of symbols from the language L. Yeah, so, but these are mean interpretational symbols. Okay, so, and this is, yeah, whatever said. We will only consider countable structures in this talk, so I will not go into computability on uncountable objects, though it can be done. You know? So this is a countable set, some subset of the natural numbers. Subset of omega. Okay, I'll keep it like this. Okay. And so we expand the language. We consider the language LM is just union L together with, well, formally speaking, again, those are constants for M in M. And so we expand the language with some new constants, or maybe we just take the same objects, so we consider them like as semantic and syntactic objects at the same time. Yeah. Okay, so this is language, and then we say that M, the structure, M is, well, we'll have two definitions. Let's start, yeah, with computable. Is computable. Computable if, well, there are two definitions. Let me just say one, and then I explain you like how to look at this from the other side. If the atomic diagram just dA of M, I will write in a second what it is. If this atomic diagram is computable, again, a computable subset of the natural numbers using a Gödel numbering of all the sentences in this language. I will write down in a second what it means. Okay, and decidable. The structure is decidable if the complete diagram C for complete of M, which I will also write in a second what it is, again, is computable. Okay, so what is the atomic diagram? The atomic diagram is the set of all sentences in this language that are true about this model. Okay, so it means phi, such that phi is an atomic LM sentence true in M. And just stay with me. I will give more intuition about this in a second. And the complete diagram is the set of all sentences, not necessarily atomic with any number of quantifiers, is first order LM sentence true in M. So what does it mean? So here we look at the structure M, and we take an arbitrary sentence, possibly with constants from the structure. Yeah? And we look at the set of those sentences. This is equivalent to saying that we can check effectively atomic facts about the structure. Yeah, so in particular, if we have a finite language, it is the same as saying that we can, the universe of the structure is computable, and it is computable to check whether or not the predicates hold or do not hold on the universe of the structure. Okay, and here it is pretty much the same, but here we do not check only for atomic facts, only just predicates, if the predicate is true or false, but any kind of facts, possibly with quantifiers. Yeah, so this is stronger. This is much stronger. Yeah, here we can check any number, like finite number of quantifiers, doesn't matter, universal, existential, anything. And here just the atomic facts. So just if we have a linear order, for example, yeah, so we have like omega, natural numbers, and some linear order defined in omega, we can only effectively check if one element is less than the other. Okay, and here we can ask, I don't know, there exists, I don't know how many elements in between such that something else happens, and so on. Okay, so these are the main definitions. And as I said, today we'll mostly talk about decidable theories and decidable models of those theories. And next time we'll go here and I will give you yet another way to think about computable structures, which is a very nice dynamic way to think about them. Okay, fine. So you can also see from this definition that theoretically, well, not every structure has to be computable, and not every structure has to be decidable. But it might happen. So it is very much a property of a particular isomorphic copy of a structure. So it might happen that the structure itself is not computable, but it is isomorphic to a computable structure. A very, very simple, maybe even a bit silly example, which still shows how this might happen, is just to take some set, let's say S is a non-computable, I don't know, a non-computable set. Non-computable set. And then we just take a structure which looks like this set and the order less than, where this is just the natural order of the natural numbers. Okay, so formally speaking, the structure will not be computable itself. Yes? What, sorry? I'm not sure. exactly. So it is. That's what I'm saying. That the isomorphism basically will give. So even though if you look at it the way it is, yeah. So the set will not be computable because just this set is not computable. But it is in reality, it's very computable. So it's easily isomorphic to an absolutely computable thing, right? Okay, but this is a stupid example, so we will not consider examples like this. So we do not want the complexity to come from the complexity of the set. Okay, so if we talk about non-computable structures, which we will not do today, but later, we want the complexity to come from the relations and functions or whatever, not from the complexity of the set. So mostly we will have structures which have the universe all of the natural numbers, or at least a computable subset of the natural numbers. And yes, so this will be the complicated part. Okay. So, and those structures that are possibly non-computable but have a computable isomorphic copies are called computably presentable, or in the decidable situation, decidably presentable. Okay. Computable presentation. Of a structure. Is, let's say, computable and decidable. Is computable, decidable, isomorphic copy of M. Okay, so this is terminology that we will use later. Okay, so the very first fact here is the existence of decidable models of decidable theories. So let's call it a theorem. Let me check the notations that I do not mix up. Okay, maybe before the theorem, let's consider a couple of examples, familiar, hopefully, examples. So, examples, the first one, the theory of dense linear orders. Dense linear orders. So the theory of the rationals. So we consider without endpoints, right? The theory of the structure. Okay, so this is a decidable theory. I will not really go through the proof of all this, but it's rather easy to see. So it's easy to see that this structure is a computable structure because we know how to compare rational numbers. Okay, but it's more than that. It is decidable, and the reason is that we have effective quantify elimination here. Yeah? Okay, so if you know how to do the quantify elimination for this theory, then just go through this process and you will see that everything is very computable there. Okay, so we can computably transform an arbitrary formula into a quantify free formula, and we can check quantify free facts very easily here. Okay, the same happens for algebraically closed fields. The theory of algebraically closed fields. Let's say characteristic 0. Okay, so pretty much for the same reason. Okay. Well, moreover, what can we say here? Yeah, so those theories are also countably categorical, which means they have only one countable model up to isomorphism. And so this is it. Yeah? And this model is itself decidable. So decidability of a model of a theory is also stronger properties than decidability of the theory itself. It might be the case that the theory is decidable, but some model of it is not decidable. Yeah, so it is not the case here because we only have one countable model of the theory. And then a third example here of something that is a theory that is not decidable, which is probably relevant in the context of reverse math, the theory of PA, yeah, the theory of Peano arithmetic. This is a theory that is not decidable, and it has no decidable models, and only the standard model of arithmetic is computable. The others are not even computable. And maybe I will talk to other people if next time we go through a proof that shows that non-standard models of arithmetic are not computable. Okay, we'll see. Okay, so anyways, the theorem. If we have, if T, a theory T is decidable, then, well, and consistent, so I will only talk about consistent theories. Okay, if T is decidable, then it has a decidable model. Okay, and the proof is pretty much the usual proof. Yeah? So the standard Hankin construction, existence of a model of a theory. The only thing that we need to do is to check that everything that we do there is effective. Okay, so let's see if I want to show at least something like maybe we will do just a sketch of this one proof, just that you know what I'm talking about, and the next proofs I will just pretty much hand wave. Well, I will even hand wave here mostly. Okay. So, what's the usual proof of this theorem without decidability, any decidability? Yeah, the Hankin construction. So we have our theory T, and to build a model, we expand the language. So we take the language of this theory, and we expand it by new constants, Ci, I in omega. And then we do the usual thing. So we build a complete extension of T with those constants, including those constants, in such a way. That we ensure that that if we have an existential formula, if the exist x phi is in our extension, then we have some witness for this. Then phi of some constant Ci is also in our extension. So basically, we take the next formula in this language, and we check if it is consistent with T. If it is, then we add this formula to our big completion, and well, whatever this formula doesn't have to have this as existential quantifier. So if it's not consistent, then we take the negation and we add it to the set. And if it is an existential formula, then we add this thing for some new constant, not yet used constant. Okay, so this is something that I assume that you know. And then we do, then we do the quotient, saying if Ci equals Cj is in our big set, let's call it theta, expanding T. Yeah, so we do the quotient, and what we get is our model, model with the natural interpretation of all the symbols. So this is the usual way to do this hand-key construction. Why is it effective? Well, because basically the only thing that we need to check there if adding a new formula is consistent or not with the theory, and we can do it because the theory is decidable. Yeah, so the theory is decidable, so checking this consistency is an effective process, and then taking this quotient for the same reason is also effective. So everything is effective. Thus, the structure that we get is decidable. Okay. So far, we do not move outside of the classic results. So what holds classically also holds effectively here. It's not always the case. Okay, not always the case. I'm not sure that we will, I don't think that we will do it today, but maybe at least I will formulate the result later that shows the difference between effective mathematics and classical mathematics. For now, let's continue effectivizing some more results. So in particular, you see here that the only non-effective question that we do here in this construction is basically asking about consistency, if a formula is consistent with what I have built so far. Yeah. So if the theory is decidable, then we can answer this computably. If the theory is not decidable, then we need one jump. With the help of one jump, we can do this, and this shows the corollary. Corollary. If T is a consistent theory, then it has a model that is such that its elementary diagram is computable in one jump of T. Model such that the complete diagram of M, model M, is computable in T jump. So basically, M is delta 02 in T. Okay, so this holds for arbitrary theories. Okay, another corollary. A theory is decidable. Well, again, a consistent theory is decidable if and only if it has a decidable model. So one direction is this theorem. The other direction is pretty obvious, just because the complete diagram of M basically also contains as a, well, not just contains the theory as a subset, but you can effectively get the theory from the atomic diagram of the structure. Okay, so this is an if and only if relation. Okay, complete theory, sorry, should stay complete. A complete theory, yes, because if it is complete, then we can effectively get the theory from the complete diagram of the structure. If it's not complete, then a theory, not necessarily complete, has a decidable model if and only if it has a decidable complete extension. Okay. Okay, fine. So now let's talk a bit about realizing and omitting types in an effective way. Okay, let me recall what types are. So this is a more theoretic definition. Okay, suppose M is an structure in some language L, and suppose A is a subset of the universe, and so this M is the universe of the structure M. Then we can define again the language L, A, similar to what we had somewhere there. So this is just the language L with the constants for all the elements from A. Yeah, so this is a subset of that set, the above. And okay, so basically we can see, we can look at this structure M as an LA structure. And we just interpret those symbols in the obvious way. Yeah, CA is interpreted as A in this language. Okay. Fine. So then we can also define the theory TA of M being, well, pretty much the same thing that we had there, like the complete diagram, but we just do not take all first order sentences with any constants from M, but only constants from here. Okay, so those are all the sentences in this language that are true about M. Okay, so this is a subset, the complete diagram. Okay, and now we can define types. Well, I hope you know those definitions, but I will still give them. So let P be the set, of LA formulas, possibly with free variables. Well, usually with free variables. Free variables, okay. Say V1 to Vn. So this is an n type, will be the n type. So then P is an, so it is not the set, it's an S set, some set. Then P is an n type. N type if P together with this set is satisfiable. Yeah, so the meaning of this is just, so we have a theory, possibly with some constants So we have some facts, possibly with constants, about this, about the structure, and then we add some more properties with some free variables that we want to be true, maybe in some other model of this. And we check if this is satisfiable. If there is such a model, and this is an n-type. So what will be an example? Examples. Let's go back to this Q and less than structure. Okay, so let's say that our set A is just the set omega. So LA is just the set, the relation symbol plus all the constants for the natural numbers. Yeah, so this is a constant for this n. And yeah, so we may have different kinds of types. For example, we may say we want our V to be greater than 1, greater than 2, greater than 3, and so on. Okay? Okay, so this is formally not in the language, but you know what I mean. You know how to rewrite this using less than. Okay, yeah, so this would be a type, yeah? So we have formulas with one free variable, so we write this variable here just to stress that we have a type in one variable. These are our constants from A that we use to describe this type. So basically here we say that we have an element that is bigger than all the natural numbers. Okay, so it is not true in this model, but it is locally consistent, so any finite subset is consistent, okay, which means that by compactness we can get a model of the theory of the dense linear orders where we do have some non-standard element that is greater than all the natural numbers. So this is one example of a type. And then another example of a type, let's call it Q of V. It is just the set of all formulas in this language that are true about in LA, that are true about whatever element. Let's say V is true about 1/2. So in particular, if we have something like V is less than 3, will be in this type, and I don't know, V is, I don't know, greater than 2, will not be here. Yeah, so, and you see those are two different kinds of type. So yeah, two different kinds of type that are true about that are consistent with the theory of this structure, and this is true even here on the element 1/2. Well, this is not true in this model, but in some other model it is. Okay, so this type will be actually true, yeah, in all models. So this is true in all models. This one is true in some models, not necessarily all. And this is yes. So this is a property of the type. Type may be realized in some structure, so meaning that all of them in some model, meaning that all of those formulas are true in a model, or it may be omitted in a model, meaning that one of those or some of those, whatever, is not true. Okay, and so we're going to talk about realizability and omitting types in the effective context. Okay, so let's see if I want to talk about this. No, I don't. Okay, so let me just go through some of those results. Okay, in particular, just from the compactness and just from compactness, from effective version of compactness, we may show that if we have a decidable theory and a computable type, then we can realize this type in a let's see, decidable model of a theory. Let's see, where do we have it? Not the mix annotations that I have here, sorry for that. You know, it must be somewhere here. Okay, yeah, so it is a proposition here. Okay, proposition. Every computable type, yeah, so this is a set of formulas. Everything is effective. Again, we can talk about computability theoretic properties of this set, so we can measure its complexity. So if we have a computable type, of a decidable theory, every computable type of a decidable theory is realized in a decidable model. Okay, so basically what we do here, we just take some new constants that do not occur in our type, and we get a consistent decidable theory if we, so let C1, Cn be new constants. And then we consider the theory which looks like T together with P, where we substitute variables with those constants. So this will be a theory, a set of sentences now, a decidable set of sentences, a decidable theory, consistent theory because this is consistent by definition, and by the theorem that we had there. This theory has a decidable model, and then when we interpret those constants, so we forget about them, basically, about those constants, and only consider the original language, then what we get is a decidable model of T. Okay, fine. Yes. You mean on this set A or? Yes. Yeah. So here I define it for. So I fix some whatever set A. So it's. Yes. Let's see. Well, the type has to be. Well, the type as a set of sentences has to be computable. Yes. Well, on A we have it pretty much automatically because we say that it should be computable type. So there must be, A itself must be also computable, but yes. So, yeah. So here we say that there exists some decidable model, so the original doesn't have to be anyhow computable. Okay. Okay, also what we have here, that every complete type realized in a decidable model is computable. In a decidable it's computable. So this is probably relevant for your question to some extent. Yeah? So if we have a decidable model, well, from the very beginning, then the type, if it's complete, will be automatically computable. Okay, so yes, complete type means that whatever, pretty much like a complete theory. So that's any, for any phi, you have either phi in P or not phi in P. Okay, so then I have something as an exercise for you. Think about it a couple of days or maybe a couple of minutes. And then if you have any questions by the end of my lectures, then we can discuss it. Okay, exercise. Yeah. Yeah. So let me check. Not to tell anything that I don't want to. Yeah, so we just required really to be in the type. Sorry, just a second. Okay, so before I give the exercise, let me recall yet another definition. What are isolated types or principal types? So we say another definition, a formula phi isolates type P if, well, everything in this type follows from phi. Phi implies all psi from this type. Okay, so, and a type is isolated if it has an isolating formula. P is isolated. Principal. if it has an isolating formula. Okay, so this is a standard model theoretic definition as well. So on the exercise is the following, that if we have an decidable theory, then every isolated complete type is computable. If T is decidable, then every isolated complete type is computable. Okay, so this is the exercise for you. Okay. So, well, basically, basically that's it. Just let me give the last also theorem that holds effectively as well as non-effectively. Yeah, the effective omitting type theorem. If the type is non-isolated, like non-principal types, they may be realized or omitted in different models of a theory. And the omitting type theory says that, like the classical omitting type theory says that if we have a non-isolated type of a complete theory, or whatever theory, then we have a model which omits this type, means that there is some formula from this type that is false in this model. And the effective version just says the same with getting decidable, computable everywhere you want, everywhere you can. Okay, so this is still everything exactly in the classical case. So let P be a computable type, computable non-isolated type. Type of a complete decidable theory. Then it is omitted in a decidable model of T. And the proof is again the same Hankin style construction, the classical construction. The only thing you need to do is to check again that you do every step effectively, and you do because your type is computable and the theory is decidable. So the classical constructions goes through. Okay, so those are results that are not very surprising, though nice. Yeah, but as I said, the effective and non-effective versions do not always coincide. In particular, this is what we will talk at the beginning of the next lecture. If you know this result, that if we have this is a classical result by Watt, I think, yes, like Watt's result, that if we have a theory that has at least two non-isomorphic models, countable models, then it for sure has a third non-isomorphic model. Yeah. So if M1, M2 are models of a theory, non-isomorphic, then there exists a third non-isomorphic model. There exists M3, model of T, and M3 is not isomorphic to either of those. Okay, so each theory that has at least two non-isomorphic models has actually at least three non-isomorphic models. Okay, so what if we insert decidable everywhere? Suppose we have a decidable theory and two non-isomorphic decidable models of this theory. Is it always true that there exists a third non-isomorphic decidable model of this theory? So this is not necessarily true. It might be the case that, and we will consider an example next time, that T is decidable and has exactly two non-isomorphic decidable models. It has a lot of non-decidable models. Yeah, so it has actually uncountably many models, countable models in general, but decidable models, it has only two, exactly two. Okay, so this is where we'll start next time. Thank you.